Okay, so we're gonna do today. We're going to talk about factorials, and we've done factorials over the last couple of days, but we just want to talk about like the let's see, it keeps going back to red. We want to talk about the arithmetic of factorial. So aim factorials. So we know, for example, we've seen, for example, I asked you to arrange the word star. How many words can you make? And you said, okay, well, star has 4 letters. So the answer is 4 factorial. We know that's 4 times 3 times 2 times 1, which equals 24. In general, we know that n factorial is equal to the n times n minus 1 times n minus 2 all the way down times to 1, right? And then we can, do some manipulations. The question is, so for example, if I say 9 factorial divided by 6 factorial, well, first, from your graphing, from your GDC, the answer is 504. The question is, can we do this by hand, analytically? Yeah, you say, yeah. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 6 times 5 times 4 times 3 times 2 times 1. You cross all those out because this is old school division, and the answer is 504. Well, this should get you thinking, like, do I need to write all these numbers out? Can I write, at 9 factorial a different way? And the answer is yeah. You could say, you know what? Oh, come on. You can say 9 factorial is 9 times 8 times 7 times 6 factorial. And that makes your computations a little bit easier. So suddenly becomes 9 factorial over 6 factorial becomes 9 times 8 times 7 times 6 factorial over 6 factorial. You can cross those out, and you get the same answers a little faster. Now, so we come up with the idea, we can see that n factorial is actually equal to n times n minus 1 factorial. And so the question is, does factorial have an arithmetic that we can use? And the answer is no, it doesn't. We do know that n factorial divided by n factorial equals 1, and we know n factorial equals n times n minus 1, but everything else, it doesn't work. So let's just test this out. For example, 2 factorial plus 3 factorial, does it equal 5 factorial? Well, does it equal? And we know it doesn't. 2 plus 6 does not equal 120. So that's out. It might be true. I'm sure I can find some example somewhere to prove that works. But in general, if you find one counterexample, the whole thing's out. How about 3 factorial minus 2 factorial? Does that equal 1 factorial? And so, 6 minus 2 equals 4. It doesn't equal 1. This is out also. How about multiplication? How about 2 factorial times 3 factorial? Does it equal 6 factorial? Well, once again, no. Because what's 2 times 6? That's 12. That clearly does not equal. So it's out. Nope. And then we know division doesn't work. 6 divided by 5 is not, we don't have a fraction at factorial. So division doesn't work. So there's really no good arithmetic for factorials. So what we can do is manipulate. So an example in the book is n factorial divided by n minus 3 factorial. So how are we going to manipulate this? Any suggestions? Well, we can write it out. N times n minus 1 times n minus 2 times n minus 3 factorial over n minus 3 factorial. These go out. We're left with this polynomial. It's a cubic. We're going to leave it factored because we're going to need it factored, right? Another thing the book might do is, ask you where fractions came from. And I kind of like this. I like this. So they say, how do you represent 10 times 11 times 12 as a ratio of factorials? And I like this because we can turn this into like a probability problem. We can turn this into a combination problem. So 10 times 11 times 12, you say, oh, you know what? Like that reminds me, all those, we chopped off all the nines. So it's like 12 times 11 times 10 times 9 factorial over 9 factorial. So this is 12 factorial over 9 factorial. And we're actually going to see this actually represents something we're interested in the next unit. Once again, what else can we do with factorials? Not much, but we can introduce older topics like factoring. So for example, you might get the question 9 factorial minus 7 factorial. And you might say, well, I don't want to do all those computations. And the question is, can you do this without a calculator? If this shows up, which not, but if it ever shows up, you say, you know what, I can do this with a calculator. So you look at this, you go, you know what, do they both have the same term? You go, oh, you know what, this is 9 times 8 times 7 factorial minus 7 factorial. I can factor out the 7 factorial, leaving me with 72 minus 1. Final answer, 71 times 7 factorial. So this is another big thing in this course, breaking down polynomials, breaking down functions into its components. So we have 71 times 7 factorial. The last problem they give you in the unit is one. They make a mistake in the book, actually. They ask you to simplify. They say at n plus 1 factorial, minus n factorial plus n minus 1 factorial. They actually dentally set it equal to the previous one, but we're fine. The idea is just factor it. And so is there something in common in all of them? And the answer is yes. Rewrite all of these as a fact with a factor of n minus 1 factorial, pull out the n minus 1 factorial, and see what you're left with. So for example, I'm going to write this as n plus 1 times n minus 1 factorial. I'm going to write the next term as n times n minus 1 factorial, and the last term is already an n minus 1 factorial. I'm going to factor out an n minus 1 factorial, and that's going to leave me with, let's see, we have n squared plus n minus n plus 1, and we get the final term, n squared minus 1 plus 1 times n minus 1 factorial. Once again, the unit's just about manipulation. The last thing I want you to think about before I have you do the problems in I think it's 1C, it is a 0 factorial. What does that equal? And that's it, 1C.